standard input to standard output, I can convert my standard input to my eigenbasis input, and then move across to eigenbasis output, and then go back to standard output. So I'm going to let the matrix S be 1, 3, 2, 1. Is this B to S or S? Is this, yeah?
B to S.
This is B to S. So this is
That's
this one. And this one then would be S inverse.
Yes.
And the special ratios is when I'm in 1 to 3, however many 1 to 3s I have gets increased by 10%. So 1.10, 0, and 0, 0. So what we get is going straight across, doing this matrix. .86. Actually, you know what? Let's just call that matrix A. And the traditional name we give for this matrix is D. So for forming A, if I have a standard input and hit it with A, that will give me the standard output. It's what I can do is I can take my standard input, change the basis to the B basis, do the D, and then come back up with S. So we're going to focus today's lecture on the mechanics of starting with the matrix A and then finding the S matrix and the D matrix. So what we're going to essentially do is find a better basis for the transformation. And by better basis, one where the matrix that represents inputs and outputs relative to that matrix is diagonal. The only non-zero entries are along the main diagonal. And then just one thing we have to be careful of. Let's say we ended up with an S like this. What's S inverse? Okay, remember, it's 1 over, and then 0 minus 0. So, quick name, it's, what do we call the lambda? Eigenvalue, and 1, 3, eigenvector. So the eigenvectors are going to be dropped into the S matrix. We want to have an S inverse, so we can't have 0, 0 as an eigenvector. 0, 0 can never be. So, let me give you a brief reminder. Now go down. So I'm just going to tell you right now that for the matrix A, 1, 2, 2, 1, lambda equals 3 is an eigenvalue. 1, 1 is a corresponding eigenvector. And so what that means, if I do 1, 2, 2, 1, times 1, 1, what's the answer going to be? And you can get that exact same answer just by doing the eigenvalue times the eigenvector. So your book puts finding eigenvalues in 7.2 and finding eigenvectors in 7.3. I want to do both of those together. So we're going to do 7.2 and 7.3 together.
started this last time, right?
Yeah. Yeah, I think
Oh,
it was-
yeah.
we did this.
Okay.
Yeah,
Okay,
can I see it?
So yes, so somebody,
Wasn't
I
that in
haven't
the book?
got it, so,
So we actually stopped at,
That's why.
yeah, okay, yeah, no, I was asking what the, last thing we did was.
the last one.
Somebody said this, or somebody said, you got it?
We did that exact example.
Good, how far did we get?
We got all the way into the end where, so we found the eigenvalues. If we're given a matrix, you said find eigenstuff.
Got it, so can you do that?
We found our eigenvalues and we found eigenvectors.
So if I give you a 2x2 matrix, you can find the eigenvalues and eigenvectors?
Determinant matrix minus eigen times lambda.
Yeah, oh, okay, cool, okay.
So we did do that. Sorry, yeah. And then you started on the homework end. So given a 2x2 matrix, we were given 6, 2, 3, 7, and we were told to find the eigenvalues, and then from the eigenvalues, we were told to find the eigenvectors.
Got it,
So that's what we're doing.
okay. Thank you. Okay, so this is where we ended?
Yes.
Okay, you sure?
Yes.
I don't know. Hopefully the review was good. Okay, so I need some determinant to be 0, right? What determinant?
Matrix minus.
So the A minus lambda I. And lambda I is going to look like lambda times 1, 0, 0, 1, which is lambda 0, 0, lambda. So essentially we're going to have 6 minus lambda 2, 3, 7 minus 3. Okay, then we do the crisscross. Some people call it the determinant. And let's see, that would be 6 minus lambda.
7 minus lambda, and 6.
You want that equal 0? I carefully picked these examples so you wouldn't have to use the quadratic formula. Put them off. And
9.
so far so good? So then what we do with these is for lambda equals 4. I erased the matrix. What was it?
2, 2, 3, 7.
Wait, 7?
What was that? So to say that lambda equals 4 as an eigenvalue means we've got a vector different than 0, 0 that makes this true. So in other words, we're going to have 6x plus 2y equal 4x, and 3x plus 7y is 4y. Solving equations, the discipline is to get all the variables on the left. And what we're hoping here is that we end up with essentially the same equation.
The matrix could be 6, 3, 2, 7. 6, 3.
Oh, no. How can this work then? Okay.
Yeah, no.
Hold on. So that's a 6. What's this entry?
2.
True. Yeah, you're right.
You're right.
Yeah.
And then 3 was 7.
I'm learning a lesson this evening. You I should trust, you I shouldn't trust.
You wrote that today. Maybe the last time you did that.
I have no clue. I'm gonna keep doing this one.
No, this is right.
So far, this is good. So, in other words, this is x plus y is 0. And essentially, that just says x and y are the same magnitude, but one's positive, one's negative. So I can use as an eigenvector -1, 1. So let's collect these over here.
Or 1 and 1, yeah.
Or 1, -1, or 2, -2. In fact, anything. Just be careful. Don't say 0, 0. Any of those other ones are okay.
It's an eigenvector for the eigenvalue.
There you go. So for eigenvalue, lambda equals 4, -1, 1 is a corresponding eigenvector. And I haven't used these words. We can actually talk about an eigenspace. So if I look at all multiples of this is going to be a subspace of R2. And we'll do the whole process again with lambda equals 2.
Number equal 9.
What's it?
Number
Oh, 9.
9. 4 and 9, yeah.
Or 9.
Oh,
9, yeah, that's
yes.
what I said, 9. That would have been a disaster. Let's make this work.
So x minus 2y equals 0.
Same equation? Okay, I'm going to show you a trick. I think I showed you this trick last time, but I want to practice it a bit more for the next section. Is 3 and 2, what's the common denominator? 6. So what I can do is I can, if I plug my value into this, if I let x be 2 and y be 3, you see I'm going to get a 6 and a -6? So lambda equals 9, and it's our corresponding eigenvalue, or eigenvector, could be 2, 3. And for the next section, oh no, actually no, I take that back. We're going to put that on hold. So if I give you a 2 by 2 or a 3 by 3 matrix, or any size matrix, you know the process for figuring out the eigenvalues and the corresponding eigenvectors? You do A minus lambda I, so just take the main diagonal, subtract off lambdas, calculate the determinant, set it equal to 0. The solutions to that are going to be your eigenvalues, and then you go through this process to get the eigenvectors. Cool? So let me show you an application. So this will be 7.4. So imagine that you've got two groups of people, either be Democrats and Republicans, or Catholics and Protestants. I'm going to draw a diagram here representing how things change over time. So the idea is, let's say X's are the Democrats, Y are the Republicans. So if you take all of this year's Democrats, half are going to stay Democrats, and half are going to become Republicans. And if you take this year's Republicans, a quarter are going to stay Republican, and 3/4 are going to be Democrats. So. First of all, you see this is going to be a closed system. So if I take all the x's plus all the y's this year, and then I do all the x's plus all the y's next year, it's going to be the same number. So, actually, let's just do an example. So we have 100 x's, and we have 100 y's. So that's this year. Next year, out of these 100 x's, how many stay x's? 50. And 50 go here. And the y's in blue. So we're also going to get some x's because they defected from the y's. So how many y's turned into x's? 75, right. So there were 100 y's, 3/4 of them turned into x's. And some x's became y's. How many?
50.
Oh, we already have that throw.
You have 25.
Yeah, I've got 25. I already want to go. Yeah, right. So it's next year's 125 x's and 75 y's. So how many people did we start with? Total number of x's and y's?
200.
200. And next year, how many will we have? 200. So, and then there's going to be some shuffling next year, shuffling the year after that. But with the way I pick these numbers is the total population. There's always going to be 200 people in the system.
If both the columns add up to 1, is the matrix always closed?
Yeah, we're going to talk about that. Absolutely right. So, short answer, yes. I'm going to give the product to you. So some words, as we call this a transition diagram. And not too surprisingly, we're going to turn this into a linear algebra problem by making a matrix. So just like we did with the coyotes and the road runners. So how do I get next year's x's? How many of this year's x's become next year's x's? 1/2. And how many of this year's y's become next year's x's? 3/4. And next year's y's, the x's,
1/2,
and
1/4.
And then, as you correctly pointed out, it's the way we can, as a linear algebra way to recognize that it's a closed system, is all the columns add up to 1. Okay, so we've got a special name for matrices that have that property. You don't have to know this, I'm just going to throw it out there though. Is we call that a stochastic matrix. Stochastic, spelled right. Stochastic. It's a big math word that means random, essentially. So, different class, you could actually prove this. I'm just going to write it as a fact. And we'll just be working a specific example. But if you have a stochastic matrix, so a matrix that represents a closed system, then lambda equals 1 is always an eigenvalue. And all the other eigenvalues are between -1 and 1. So, let's give a name to this. I'm writing it down. These out for you. And I have every confidence that you can do this yourself. Do you agree? Do you know the process for taking that matrix A, finding the lambdas and their corresponding eigenvectors? So I just did all the busy work for you. That's what it comes out to. And as promised, we're always going to have a lambda equals 1 because it's stochastic. The other one's going to be -1. So I'm going to do this problem 3 different ways. If I want to go n years into the future, do you see that's just multiplied by a to the n? Can we talk about that? Go. Talk?
Yes.
Okay. So, year 0 is 100, 100. And the way I get to year 1 is I do the transition matrix times 100, 100. So this is the year 1 population. The way I get to the year 2 is I take the year 1 population and multiply it by A. So you get from 1 year to the next, I multiply by A. This is the same as A squared times 100, 100. Year 3, get it with A again. So n years in the future is going to be a to the n times 100, 100. And then, in the long run, and if we're really trying to figure out what happens as n goes to infinity. So we're not going to lose people, we're not going to gain people. But in the long run, the populations are going to kind of settle down. We'll talk about what they settle to. I'm going to do this problem 3 different ways. So the first way is I'm going to think about the 2 eigenvectors as making an eigenbasis. So I'm going to multiply, I'm going to break that 100, 100 down. I've done this for you. If I had lost my notes, you could fill in the blanks, right? A little bit of work, 40, 20. You either set it up as a system of equations, or you can do a change of basis. We go 100 years in the future, or n years in the future. So I'm going to multiply that 100, 100. By a to the n. Change this so it looks a little bit nicer. we carefully chose 3, 2, and negative 1, 1, because multiplying 3, 2 times A is the same thing as multiplying 3, 2 by what number?
1.
Yes, I lost it already. So remember the 3, 2 corresponded to lambda equals 1. So this expression is 40 times 1 to the n times 3 plus 20 negative 4 to the n negative 1, 1. As n goes to infinity, what happens to 1 to the n? 1, 1 squared, 1 cubed, 1 to the 4th. Where does that sequence end up? No. 1, 1 squared, 1 cubed.
It ends up at 1.
It does end up at 1.
We hope.
I bet. And what about negative 1/4 to the n? Where does that end up?
0.
That ends up at 0. So as n goes to infinity, we have 40 times 1 times 3 plus 20 times 0 times negative 1, 1, which is 120, 80. So the long-term distribution is every year it's getting closer and closer to 120 x's and 80 y's. So far, so good?
Yeah.
It's method 1.
Wait, doesn't it overshoot that in its first year?
Oh yeah, and it'll settle on that. So the second year is going to be closer than it was the first year.
But it doesn't just move towards it, it moves past it.
Every year is closer than the last. But you're right, it's, I mean, if we look at the x's, so this would just be n and x. So it's not really continuous, but if it was, it's kind of that way to describe it.
That's interesting.
So it does, it overshoots, and then some of the x's defect. But it is, every step is getting closer than the previous one.
But they're the most Democrats in the year 2, or year 1, I guess.
Yeah. And that's kind of cool when the math is not what you expected. So method 2. Show you a cool idea.
This is method 1 for just finding the long-term distribution.
Exactly. So I find the long-term distribution. We find that 120, 80, 3 different ways. Each one shorter than the last. So let me show you why. It's the same idea we had before. But there's a nice algebra way to write this. So if I break A down into its S, D, S inverse factorization, then when I do A squared, it's S, D, S inverse times S, D, S inverse. But what happens when the S inverse hits the S?
1. Yeah.
1, or the identities cancel each other out, and I'm left with S, D squared, S inverse. And A cubed is going to be 3 copies of SD, S inverse. And we're going to get some canceling here.
You choose 3 as.
Very good. So, what do we know about D? What type of matrix is it? It's a diagonal matrix. If it was easy to square a diagonal matrix, then this would be a useful factorization. So let's see if it really is useful. Square diagonal matrix.
Number two.
I want to pick different numbers.
Nine.
Good. And notice that 9 is the -3 squared.
Zero.
0
Zero.
and
25.
yes. So it is easy to square a diagonal matrix, right?
Yeah.
So let's do our example. It's our A was 1/2, 1/2, 3/4, 1/4. So there's all the eigen stuff. So do you know how to use the eigen stuff to get the S in the D matrix?
Yeah.
Good. That would be D first.
1, 0, 0, negative 1 over 4.
And the S matrix.
2, 3, 1.
Good. So it's going to look a little bad, but I'm going to write that as A to the infinity times 100, 100. Is that okay? You know I really need a limit there? So that's S D S inverse to the infinity times 100, 100. And then that we just talked about. As I can write this way. Let's actually write this out now. So my S matrix is 3, 2, 1, 1. And this would be 1/5, 2/5. And my D matrix. I'm going to do this. So let me put that infinity inside. What's 1 to the infinity?
1, 0, 0, 0.
Negative 1/4 times negative 1/4, a quarter of a quarter of a quarter of a quarter is 0. And if I multiplied this mess out, which actually isn't that bad. So what's happening when I do this multiplication? This is the S inverse times the original. What am I doing?
Converting from standard eigenbasis.
Very good, yeah. So remember that the S inverse is the S to B transition matrix. So let's do that. Let's do 3, 2, 8, 1, 1. 0, 0, 0. And
40.
let's see, 20, 40. 20, right. So that's the 40, 20 that we had before. Okay, then, what happens, well, what am I going to get when I do this? The 1, 0, 0, 0 times the 40, 20
40, 0.
is that's just going to keep the 40 and 0 out the 20. Yeah.
If instead of combining these first with the 100, 100, if we were to try to put the three 2x2 matrices together first,
Yes.
under what circumstances do you get A back out of that?
Oh, you will. So if you multiply, so this version or the original?
I meant the original. Like,
Yeah, always.
always.
So SDS inverse is A.
With exactly the same numbers, or?
Yes.
Okay.
And then I want you to remember the way matrix multiplication was originally defined. Is you think of that original matrix as as two columns. And the first number is the scalar for this. And the second number is the scalar for the second column. So this is 40 times 3, 2, which is the 128. So you see this process is what's going to happen is this matrix is going to have a 1 here and a 0 here. And then that's going to pull out it's going to zero out whatever coefficient we had for this, and it's just going to extract this one. So what we know is in the long run, that's method 2. Method 3, get this by quickly, is in the long run, the population is going to have a ratio of 3 to 2. 3 x's for every 2 y's. So let me write this down. No, I keep losing that. So in the long run, it's going to be some multiple of 3, 2. And total population. Median population. So what I need to do is take 200 people and divide them into a 3 to 2 ratio. So there's 200 people in a 3 to 2 ratio. What are the numbers? 120. If you want to make a system of equations, is x to y is 3 to 2. And for every 3 x's we have 2 y's.
Plus 1 or 2.
The next plus y has to be 200. So x to y. So 3 x's for every 2 y's. So 2 x's equals 3 y's. That's what I said. 2 x's equals 3 y's.
So what do you mean when you say the total population is the same as the beginning population?
Oh, it's that we started with 200 people, and every year we keep those same 200 people.
Oh.
So at the end, in the long run, we still have 200 people.
Question.
Yeah.
Even if your matrix doesn't keep exactly the same total population, can you use the sums of the